Very good show. Of course, we use some machine. Yeah. Yeah, we started. Pizza will be here sometime in probably the next 15 minutes. And you choose when to give the break. Oh, so yes. Don't mind. Thank you so much.
Good afternoon, everyone. Thank you for taking the talk. I'm doing something I hope I can deliver a good talk here. Folks, I know some of the faces, but not everyone, unfortunately. For those of you who don't know me, my name is Payam. I joined Cal Poly about 4 years ago, fall of 2022. Before that, I was at Colorado School of Mines. My background is RF and COM, but my major focus over the past few years has been mostly on antennas and antenna arrays and phased array systems in that area. The way I started in this field was, I don't know if I call it coincidence. I got fascinated by satellites and electromagnetic waves, and as the path moved forward, I ended up doing my doctoral degree on a new generation of reflectors known as reflect arrays. And at that time, that project was fully funded by a NASA program for their Mars mission. And I ended up being an antenna expert. But my core interest has always been electromagnetic waves and the fundamental physics behind it. But as an engineer, of course, you apply that to design devices that you would need. And in this case, I'm very happy to talk a little bit about antennas. For those of you who are in our electrical engineering department and have taken courses like 335 and 402, I don't know how you felt about waves. It seems it's complex. Math is going to make you crazy. Antennas, the math gets more crazy. And if we want to focus on a math type of lecture, I don't think I'm going to excite you to pursue this path. So what I want to do is talk mostly about some basic physical properties of how antennas radiate and how this would work. So first thing, antennas are basically transducers. What you see here is an ideal image of a waveguide that sends a signal to a tapered aperture, and this wave transitions into the free space. So the wave is effectively launched by this transmission line or waveguide. And the nature of antennas, at least most antennas, are reciprocal. So as far as it goes, if the wave comes to the antenna, the reverse process occurs and the signal can be collected by your transmission line and it goes to your port. Now, how antennas radiate is a fundamental physical concept. Rated currents causes the radiation to occur. And as you know, since the current, an accelerated charge causes radiation to occur. And as you know, since current is charged over time, this translates to a time varying current. So if you have a device that has a time varying current, it can create a radiation. Without, as mentioned, going into the math, perhaps I can explain it with this graph here. Assume you have an isotropic charge here at point A. If this charge accelerates to point B, what's going to happen is this. When it was at point A, it creates isotropic radiation around the charge, or at least charges exist in a spherical manner around it. When it accelerates to point B, and if as you have, the assumption is it accelerates to point B, then it continues on its acquired velocity. At that point, another sphere you can imagine would be created, which surrounds that point B there. I note that these are not to scale. But what happens, as you can see in terms of the field lines now are bending. This effectively is creating some form of disturbance as far as the electric fields are looking at it. And this disturbance propagates outward. So as far as a radiation concept behind any antenna is the acceleration of the charges on that device. And of course, acceleration of charge is something that is more difficult for us to do. What we can do is create a time varying current. A time varying current is the equivalent of an accelerated charge. So from a perspective of antenna engineering, what we want to do is go ahead and look at the charges that are on the antennas. A colleague of mine, a few years back, maybe, I don't know, maybe a lot more years back, Professor Ramatsami, he's at UCLA. He tried to explain this in the form of, I don't know if it's cheesy enough or not, but he tried to explain it in the form that as an artist, if Van Gogh was creating the currents that created his canvases or his art, as an antenna engineer, we engineer the currents on the aperture of the antenna. And the manifest of the radiation pattern is the manifest of an antenna current. So if you can control the time varying current, you can control the radiation pattern that you want. As mentioned, it all goes back to that fundamental concept of an acceleration of charge, which creates a disturbance in the electric fields. One way to explain a simple antenna, specifically a case of a dipole antenna, is this. If you have a dipole antenna, and for those of you who are more familiar with transmission lines, you know you will have standing waves occurring on the transmission line. Now, if you bend the two arms of the dipole in a way that this distance from here to here is 1/2 wavelengths, what's going to happen is, and I will show you in the next couple of images how it's going to occur. So when I'm at t equal to 0, we're going to assume that this here is positive and this here is negative. So as a result of it, the electric field lines would close from top to bottom in this manner. As this propagates further, the same process occurs. This is at 1/4 period. But what's going to happen on a transmission line is at the point where we reach 1/2 period, the polarity here and here would switch. So that loop would close and a new loop starts forming that starts propagating outward. So this process is effectively that time varying current that creates the radiation. So folks, I was told that when the pizza comes, I can pause. So I'm going to pause and we can perhaps grab some pizza, please.
Whoever's on the right side of the room can always start zigzagging your right thing.
Folks, is it positive?
That's all right. You can keep going. The Zoom can keep going.
If you guys want keys on the bottom.
Usually we have more tables for this.
Professor, please ready? Are there slides available anywhere?
Yes,
I
we can
shared
put
it
them-
with Tyler.
Yeah, they're posted in Discord on the events section. Go to the, thanks.
I don't know.
They're on there. As well as the MSS file.
Professor, so I'm taking transmission lines right now, and we usually deal with we're like finding like reflection wave coefficients and all that stuff. Is this load open? Is it like an open load?
It's an open circuit transmission line.
So
So on the left-hand side, the assumption is the transmission line goes to infinity.
yeah,
And on the right-hand side, the transmission line is open and bent.
yeah.
Can I put a pizza box on here?
And you said if the bends are half a wave or like
The total is half wavelength
the
from here to here.
okay, yeah. And that will cause waves to propagate.
I mean, it creates these field lines. So what if this is 1/2 wavelength? This is quarter wavelength, right?
Yeah.
And what happens in a transmission line? Remember the standing waves?
Yeah.
The repetition period for standing wave is what? If you have a regular line, it's land over, right?
Yeah.
If you have a transmission line that has standing waves, then it's land over 2.
Yeah.
This is exactly why that occurs. Land over 2 is that period of standing wave. So that corresponds directly to how a dipole.
Okay. I'm definitely gonna study these slides. It's a little bit more.
I wonder if I should
Not about people, but when you have like the oscillating electric field, as it goes from like the positive orientation to the 180 degrees rotation, so is the maximum set for that state dependent on the like
Excuse me, Lam.
Just like instant.
Nice. Very good, thank you. Does anyone else sign up with the entitled workshop that hasn't put their name on the sheet?
Okay, and is the flip side right? Has someone put their name in it just because the sheet was passing around? Okay, we have one.
I need to be on that sheet. I've already filled out the.
There was an announcement on Discord saying, this is the entitled workshop. There's a Google form that says RFP for the entitled workshop. And if you fill out the Google form, your name should be on the sheet.
Oh,
Okay,
yeah.
so raise your hand if your name is not on the sheet. You did fill out that Google form.
Hey, I want to keep listening to myself.
There are currently 15.
If there's, well, if there's, if people don't show up.
It is okay.
Greg is.
Like, I'm willing to bet.
Greg Phillips is the fitting bird food.
Yeah.
How are you?
Nice to meet you. Jim. I'm Nayeri. Oh, look, professor. Professor Nayeri. Nice to meet you. I don't know if you're classes. First time, right? Yeah. You're electrical engineer? Yeah, but I've heard of you.
Like what's gone?
Yeah.
Yeah.
Oh, I'm good, thanks, appreciate it.
Yeah, so if you want to, but,
Again, sorry for the interruption.
All good. I hope the recording isn't going to be bad. I paused it.
No, that should be fine then.
I'll resume once.
We just chop it up anyway.
You do? Oh, yeah, software like that?
Yeah, we usually download the video file, and I mean, I personally use DaVinci Resolve. It's a huge piece of software. If you're only doing like chopping video, I don't recommend it. There are other software that you can use that's way more nice. I can
do that.
Like, yeah.
Oh, yeah, you give me a heads up when it's good to start.
Sure. Yeah.
I will not.
There's a pizza over there.
Yeah, bring that over. I'm assuming it's just cheese or fat.
That's part.
Oh, okay.
Is there anyone else who would like to grab pizza? Okay. If not, there's cheese over here. Feel free to grab some after the meeting, please. Grab one myself.
You guys actually go to the rock.
I'm gonna share what's yours. Yeah. That's what I was thinking, but. Yeah, if you can't, like, there's no pressure. I was gonna figure it anyway.
All right.
So, folks, let's resume. So the basic concept of the variation of current, as mentioned, causes radiation. But of course, this is just for a dipole, but any type of antenna operates based on the same principle. As far as it goes, there we go. There are different types of antennas that can be designed. The two main categories of antennas are wire type antennas, such as the dipoles and monopoles, or the log periodic dipole, or the Yagi-Uda antenna that you potentially have seen. The other category of antennas are fall in the range which we call aperture antennas. You analyze them by studying the electric fields and magnetic fields on the aperture of the devices. But I mean, of course, the current directly relates to the electric and magnetic fields, but due to the nature of these are referred to as aperture type, and these are referred to as current type. So as an example, I have a printed dipole for you here. When I mean printed dipole, you can imagine that in this case, we printed this on a PCB. And beneath it, we are feeding it with an SMA connector, which the feed pin connects to one arm and the ground plane connects to the other arm. That basic principle of radiation, as mentioned, is observed in this one. And this would create an apple-shaped type of radiation pattern that is associated with these types of dipoles. Now, I'm not going to go over balance and other things that are needed for a dipole to operate properly, because we are primarily focusing on monopoles in this case. But as you can see, the time varying current results in an electric field distribution around your antenna. Similarly, these are an example of aperture type antennas. So in this case, it's a printed microstrip patch antenna. The electric field is created beneath the aperture, and as a result of the spacing, the fields head up in phase and create a bore-side pattern with good gain, typically 7 to 8 dBi of gain for a patch antenna. So as far as it goes, antennas, depending on how much energy they can point in one direction, they would have certain directivity factors associated with them. Typically, antennas that have gains below 10 dB or so are categorized as low gain antennas. Dipoles are a good example of that. Monopoles are a good example of that. Patch antennas are good examples there. And of course, they have a lot of applications. Higher gain antennas between 10 and 20 dBi are typically going to be horn antennas, spiral antennas, that type of antenna that can have applications such as base stations. And of course, if you're interested in long distance communication, typically the technology is going to be something like a reflector dish type of configuration that provides much higher gain. For example, gains of 90 dBi and so are used for a lot of deep space type of communications due to the extremely long distances we're talking about. So folks, as mentioned, the slides are available to you, and I believe everybody knows where to find them. I don't want to go over all the material in the slides. I want to more focus on some of the basic things. So I'll skip this slide, but there are some factors associated with the radiation pattern, directivity, bandwidth, beam width, and other things that, with respect to antennas, has to be discussed. One thing that I want to show you, again, without going over the derivation of the math, is what we refer to as a Hertzian dipole. When we talk about point sources, of course, point source is an idealized fictional thing. We don't actually have a point source. But if we have a small antenna, then you can assume there's a current on this dipole antenna. Now, this is a very small antenna. It's commonly referred to as a Hertzian dipole. And we're going to assume our classic voltage source, or say, in this case, current source excitation. So it has a magnitude I naught and a cosine omega t function. So, I mean, in phasor form, you can also write it like this. Skipping the math, you can calculate the auxiliary vector potentials. And then I'm going to show you a lot more math. And finally, you would come to some equation that is very fundamental. This term shows up in all antenna radiation patterns, and it's what we refer to as a spherical propagation factor. For those of you who are familiar with basic transmission lines, you recall the E minus JKZ term that you used in your transmission lines. That denotes propagation in the Z direction. In this case, we are saying it radiates in the R direction because usually you analyze antennas in the spherical coordinate system. So I have a wave that goes in the R direction, but look at this R that shows up in the denominator. This directly is going to cut the magnitude of your auxiliary vector potential by that factor R. In other words, the further you go away from the antenna, the more you're going to lose gain. Of course, in this case, it's voltage. We haven't talked about power yet, but you can imagine if this is what I'm losing for this auxiliary vector potential for power, it's going to be R squared, which means that if you're away from your antenna, your gain is going to drop significantly. So again, a lot of fun math for you guys to enjoy, but this is the expressions that we can analytically derive for a Hertzian dipole. So note that in this case, I have a bunch of terms, but this is where some approximations can be made. If you say R is very large, then I can potentially consider some of these terms to be negligible compared to the other ones. So if R is very large, R cubed is going to be very large. So I can ignore that one there. And R squared is also going to be large compared to KR. So I can potentially ignore these two terms. When it comes to H phi, I can ignore this term. So if I look at it right now, E theta would just have this first term, and H phi would only have this term. And if I ignore R squared and R cubed there, I can ignore it here as well. So this term also completely goes away. In other words, if R is large, my electric field is only going to be in the θ direction. My magnetic field is only going to be in the phi direction, and my wave propagates in the R direction. That is the far field condition for any type of orthogonal wave. And for those of you who have taken 402, I trust you recall transverse electromagnetic mode, TEM. This is exactly TEM. So E and H are orthogonal, and propagation direction is orthogonal to those. So, as mentioned, there's a lot of approximation that we would do because of the nature of when we discuss far field. A far field is the condition that the waves are so far away from the antenna that we can basically ignore the source by itself. Mathematically, bare minimum, we talk about 2D squared over lambda is going to be your far field condition, where D is the maximum size. In this case, if it's a dipole, D is lambda over 2. Now, for those of you who did not enjoy all those line integrals and other fun stuff you did in your 402, in practice, if you become an antenna engineer, you're not going to be sitting in the office solving integral equations. You're actually going to use CAD software. This example that I'm showing for you was done by software that, again, has a free license for students. It's Alter Fico now, and as you can see, it models the radiation pattern of a Hertzian dipole, and you can use it. As far as the main focus I wanted to have today was to actually show you some CAD model and how you would do it with that software. But as mentioned, the power associated with the antenna can be computed. But if you recall, your power expression is simply going to be very good. Similar to what we do in circuits, where the average power is 1/2 of the real part of V times I conjugate. The power here is 1/2 of the real part of E cross H conjugate. So I can compute the power. But as mentioned, this expression of E minus JKR over R shows up in both E and H. So in terms of power, your power is going to drop by a factor of 1 over R squared when you look at the power associated with any antenna. And I have a lot of these fun equations for you to look at it on your own. So as mentioned, any type of antenna has a certain directivity associated with it. An antenna points the power into a certain direction. So effectively, it's a spatial type of filtering. In the case of an antenna, typically you have a main beam pointing in a certain direction, assuming it's a symmetric type of radiation pattern, which mostly are. You see I've marked these 2 points as the half power point on the right, half power point on the left. This is going to be where the power drops to 1/2 or minus 3 dB down from the peak that you have. And due to the nature of the currents that are on any antenna, it's possible you would have lobes associated with it. Typically, this first lobe is going to be the highest one, and we talk about it in terms of a side lobe level, well, how low the side lobe is for any given antenna. Remember, if your antenna especially is used to track a target, it would detect it here. But if your target is here, it would also detect it. So how low that side lobe is could have some important implications. In case of some antennas, such as Yagi-Uda or LPDA or types like that, you may have a strong back lobe here as well. So again, you have to pay attention what type of radiation pattern you're looking for any given application. So these are basically the three types of radiation patterns that we expect. The isotropic types of antennas, as mentioned, aren't really practical, but from an educational perspective are very fundamental. And if you get introduced to antenna arrays, a lot of the analysis starts with using isotropic type of radiators. This type of antenna, the dipole type antenna, is the one that we are going to talk a little bit about today. And these are higher directivity antennas. As you can see, they point the beam in a very accurate direction. Depending on the size, those would be impacted. But just so you know, with large spherical reflectors that are used for some applications, we can have half power beam widths in the order of 0.1 degrees. So that's extremely highly directive and of course has its own application. So there's a measure which is known as directivity, which is effectively the power associated with the main beam over the power of the entire antenna. This is known as directivity of the antenna. The more directive an antenna is, its directivity obviously increases. Your typical dipole would have a directivity of about 2.15 dBi. And as mentioned, patches may have 7 or 8 dBi, and reflectors can have much higher directivity associated with them. Okay, so folks, I wanted to bring the focus to what we want to do today with respect to dipoles and monopoles. So I have some slides here that shows the basic concept, and then we would primarily focus on some calculations and some HFSS models that I have. So your typical half-wavelength dipole, as mentioned, you're typically going to feed it with a wire, with a transmission line here, and commonly you're going to have a balun to ensure a good matching. Keep in mind that there are mismatch would occur in the case of a dipole. If you have your dipole here, the typical dipole would have an impedance of 73 plus 42.5 ohms. But you are feeding it with a 50 ohm line. So for those of you who are familiar with transmission line theory, this is going to be your load. So you obviously would see a reflection occurring here, which the value of it is going to be your ZD minus Z naught over ZD plus Z naught. So in other words, your dipole would not be perfectly matched and would cause some mismatch to occur. Now, same deal, when you're designing a monopole, which is what we want to do today, is you're going to go ahead and have your coaxial line directly feed to an inner conductor, but you're going to add a ground plane there. Now, your typical dipole should have a length of λ/2. But depending on the frequency you're operating, that may be large. So it's possible to have dipoles that have shorter length. The best solution is generally what we call a monopole antenna, where you would have the ground plane like this, and this, which has a length of λ/4. Similarly, you're probably going to feed it with the coax. If I recall correctly from what I discussed earlier, you folks are planning to use a BNC connector to connect it, right? So you have something like this. The way this works, if you assume you have a current in this direction, and this ground plane is a perfect electric conductor, image theory shows that you would have an image of this current here. So the aim of this ground is to basically mirror it here, and the current follows the correct direction. So this would allow, for example, at your observation point, this is how it's going to look like. These signals would add up in phase, and it would create basically like a dipole type radiation pattern. However, an ideal monopole operates on a ground plane that is infinite. That means there is no signal on the bottom. So if my dipole had a gain of 2.15 dBi, the existence of an infinite ground plane would add that by about 3 dBi. So in the case of a monopole, the gain is typically about 5 dBi. Now, this is if you have an infinite ground. If you have a finite ground, which is the way we are going to design our monopole here, this gain would be reduced significantly because the ground plane has an impact. Now, one question, and this is something that I would, we're not going to discuss a lot, but you can imagine operating at a much lower frequencies, for example, HF type of frequencies. The antenna size becomes prohibitively large. So the question is, well, can't I have a shorter wire and would it work? The answer is yes, but there's an issue with that one. Typically, this is a decent impedance. When you cut the antenna in half, in this case, Landover 4, this impedance almost gets cut in half. As you keep reducing the size of the antenna, its input impedance becomes smaller and smaller. It may even go below 1 ohm. If that's the case, you're going to get a huge reflection due to the mismatch between your antenna and your, of course, feed setup. There are ways to fix that, but at the end of the day, also the current distribution is not going to be great. In the case of a dipole antenna, the current distribution on the antenna is going to look something like this. And in the case of the monopole, it's going to look similar to that one. But as the antenna becomes shorter and shorter, the current looks like this, and eventually the current is going to be really small. So you don't have much of a time varying current, and you have a huge mismatch problem. So electrically small antennas are a challenge to design. There's a limit known as choose limit that dictates it, but generally speaking, their efficiency is low. So as far as we are concerned, based on my conversation earlier, we are just going to talk about UHF, VHF type of antennas here today. So I have a couple of those examples to show you. Once I go over the slides, I'll open my HFSS model and I can show you that in more detail there. But first thing we have to do, we are going to feed this antenna with a transmission line. In this case, I'm just sketching the basic model of a coaxial cable. And if for those of you who have taken courses in 335, at least I believe this should be covered, you can calculate the characteristic impedance of a coaxial cable if you know B and A, where A is the radius of the inner core, B is the inner diameter of the coaxial cable, and in this case, we're assuming the coax is lossless. Under this condition, if you know what wire you're using, you can calculate the shell dimension that you need. So in this case, I believe in my model, I used a 1 millimeter radius for A, and I calculated B to be, I think, 2.3 millimeters or so. And this is what I set up. So this is my coaxial cable that is has a wave port here, and it's directly feeding this long wire. This is the 2-meter band. So I didn't do any fancy calculations with it. So for the 2-meter band, if you want Landover 4, then we are talking about 50 centimeters for the length of that monopole. And that's exactly what I've used there. So this is a 50 millimeter wire. I believe you plan to use a nitinol wire for your experiments, and I don't know what diameter you're using there. As far as I know, in the HFSS material library, I couldn't find nitinol, but its conductivity is high. Its resistivity was pretty good. So I think from a perspective of determining your dimension, you really just need to tune the length. You don't have to worry about the material. You can just use copper. 1 millimeter diameter. Okay. I'm using 1 millimeter radius, if I'm not mistaken. But yeah, I mean, you have the HFSS file, so you can fix that. Very good. And this is the radiation pattern, as you can tell. Note that the ground plane here is extremely small. For a typical monopole antenna, in order to get a good radiation pattern and a good directivity out of it, you typically need the ground plane to have a diameter of at least 5 wavelengths. So this is extremely small, but it does something. And you can probably experiment with it once you open the HFSS file. If you remove this ground plane, the matching would completely go away. It's going to have a huge impact on the matching. So when you're building your own antenna, you need to have something that acts as a reflector. Maybe your body, depending on how you hold it, that would have good enough impact that it should work. So you don't need to generally include this when you're building your antenna. Now, one thing that I really like about the UHF and VHF band is the 2-meter band and the 70-centimeter band have a very nice relationship. If I use the same feed and actually just go ahead and see the operation at the 70-centimeter band, this is the radiation pattern I'm getting. In this case, note that your monopole is actually, if I think I have it here, I think it would be almost 3/4 of a wavelength for the UHF band. If you're using the same VHF dimension for it, this would be like this. As a result of this, the current on the monopole would have lobes associated with it. So it would look something like this. As a result of that, you can see the radiation pattern here is a bit different than the previous one. It still is omnidirectional in the sense that the peak, you have a null, but you're still getting decent gain out of this one. So let me show you the matching. As mentioned, I didn't do any fancy tuning or anything. I just plugged in those exact numbers. The 50-centimeter line is basically my dipole. You can tweak it a bit and play with the radius a little bit. Typically, increasing the radius of a wire antenna improves its matching bandwidth or bandwidth. And of course, in the case that if you're using a BNC connector and that 1 millimeter thick nitinol wire, then you can actually plug in those exact dimensions and tweak the wire size a bit. Note that the current distribution on the ground plane at the VHF band and UHF band are also shown here. You see that at UHF band, you have a lot of edge current associated with it due to the larger size of this type of antenna. Now, this also perhaps is a bit difficult to see. Once you have your HFSS model, you can probably see it. This is the current that is varying on the monopole. And as you can see, due to the different variation of the current, the pattern shape is different. The red curve corresponds to the VHF design, which is an ideal monopole. And this one corresponds to the UHF design, which is basically 3/4 of a wavelength type of antenna. So really, by just grabbing a 50-centimeter wire and connecting it to a BNC connector, that's pretty much all you need for this Saturday. So I hope I didn't dial it down to make it so simple, but really in nature, it is pretty simple. So folks, on the slides, this is all I had. I want to give you a little time to ask me any questions. Nobody asked me anything yet. So if there is, and I'm happy to discuss that, and then maybe we can go ahead and I'll show you some things in the HFSS setup and how you can set up your model.
Can you go back to the previous slide and explain to us the aspirate? Because I think that will come up for Saturday. So
you're using your nano VNAs?
Yeah. So we're going to be clipping the length and trying to get it to be optimal. So you cover that would be awesome.
Certainly. You are referring to this slide, which this is your magnitude of S11. It's a one-port network, right?
Yeah.
And ideally, if I have gamma or no reflection coefficient, then in dB scale, I want to be at 0. Sorry, minus infinity. Minus infinity for dB scale. Let me put dB here. So no reflection. And the antenna is basically matched at its center frequency, but at some point, as you can tell, you're gonna say there's a threshold in terms of your matching. And I trust you've seen this in your 375 lab. Our threshold is minus 10 dB down. If you recall, 10 dB down corresponds to 90% throughput of power. So what we are saying is across this band, across this frequency band, 90% of the power gets through. So if I want to define the bandwidth, in this case, you can tell I did a pretty poor job right here. This is not matched better than minus 8 dB or so. So if you want to fix this, you have to tweak that length a little bit. That quarter wavelength is the ideal setup you have due to the impact of the quarks and the ground plane, and of course, fringing fields associated with the edge of that monopole. That number is not exact. So obviously some fine tuning could be useful there. And of course, this is dual band design, so you have the same thing here for your, this is your VHF and this is your. So Tyler, was I able to answer somewhat what you want to see?
Yeah, that's perfect. Thank you.
So I trust you're just going to go ahead and test your antennas. You're not going to measure radiation patterns, are you?
Yeah, that's correct. We're gonna look at S11 and SWR.
Okay, folks. So let me go ahead and I don't know if go for it.
Can you go to the radiation pattern of the VHF one? Yeah. I was just.
Oh, sorry, it's not showing up. Give me a second.
So the one before this one, the VHF one. Yeah. How does it make sense? Like if you're below 90 degrees, why is there still a gain there? There's a ground plane now.
Oh, I can show you in the HFSS model. As mentioned, this ground plane is so small compared to the wavelength. What you want to have is a ground plane for a real monopole, at least 5 wavelength diameter. And in that case, there would be very little field below it, and you would see a lot of diffractions. But I actually didn't simulate that, as you can tell probably here. I intentionally set it up with a student version. The student version is limited in memory. You would not be able to model something that large. So I gave you something that you can model with the student version, then it would work. But no, your point is well taken. Theoretically, an ideal monopole would have a pattern like this, nothing below the ground plane. And if the ground plane is finite, then you would get fringing fields here. But this ground plane is so small that basically the the field completely wraps around it.
So then is the impedance preserved from the dipole condition into the monopole condition, or is
Very good. Ideally, the impedance of the monopole is half this.
okay?
But this is under the condition that image theory perfectly applies, which means an infinite ground. In this case, and you can do this study for sure, the ground plane reduced the size, the input impedance changes so much, it becomes so small, you can't even match it anymore. So you do need something to act as your reflector back on this monopole for it to work, otherwise it won't. And you can test that in the lab.
I mean, typically when you attach it to a radio, the radio body and the body will act as
the ground plane. Fair enough.
Not a perfect one.
It does something.
Yeah.
If it doesn't, just maybe you can have a small sheet connected to it and it would work. Oops, let me see if I can open my HFSS file and show some stuff there to you. Oh, the screen is not.
Not gonna.
Yeah.
But when we were testing out our antennas, when we used the Keysight VNAs, it worked fine, and then we switched it to the nano VNAs, and like we couldn't get it to work, and we added a ground plane to it, and then it worked. So I think the physical size
of the VNA held.
The VNA and the amount of metal on it was like acting as a ground plane.
That's a correct observation.
So that was all actually, but so that was kind of funny.
Back to mirroring both.
The way you'll be able to see here, I don't want you looking back.
Appreciate that.
And, let's get the the sharing going again.
Yeah.
Yeah.
I don't know. I'm pretty sure they're not gonna come.
That's
The HFSS file that I shared with you.
Sorry.
This is the HFSS file I shared with you. I trust some of you may have HFSS on your computer and you can go ahead and use it. To set something up on a software like this, and this is pretty common in all areas. I mean, other software like CST and FICO are the same deal. Typically, you go to your mod, you go and you can draw different objects. In this case, you can tell in order to create what I want here, I needed to create a couple of cylinders that act as my coaxial cable. If I zoom in here, side view would be better. So in this case, this is the coaxial line that I set up. This is the side view. So what you see, this line is your basic ground plane. And this is hollow. So this matches the dimensions that I mentioned earlier with respect to the coax. So the inner diameter of, the inner radius of this cylinder that I have is 2.3 millimeters, and the radius of this pin is 1 millimeter. And as mentioned, the whole thing is just 50 centimeters long above a vertical ground. To set these things up, you have to provide a few things in the setup. First, you create your geometrical model and keep in mind that it's possible to completely go with a variable-based design. I didn't design any variables other than the length of the dipole, but you can have everything parameterized, so tweaking of it would be easy. If you want to play around with this dipole, really all you have to do is come here and play with this value of 50 ohm, and you can tune it a little bit to your liking. Now, you have to define the material property. So once you create the initial dimensions and whatever geometry you have, everything would be set up as a vacuum. But you can just go ahead and right-click on the material and assign different materials for it. And HFSS, similar to ADS, I trust some of you have used, has a huge database of materials. So most are there. Unfortunately, not this nitinol wire, but there's a lot of material you can find there. So you create your geometry, you create your material, then you have to go ahead and keep in mind that you want to analyze a structure like this, but that this structure has to be solved by solving Maxwell's equations. So you have to define a finite boundary around it. You can't solve for the entire space, at least not with this software. The way it works, typically you're going to create what is commonly known as an airbox. This is the airbox that I created around it. The airbox has to be decently large. Typical recommendation is to have the airbox to be lambda over 2 in terms of the distance from the radiating elements. But again, if memory prohibits that, you can probably go smaller. ANSYS insists that their radiation box that I'll show you is valid up to lambda over 10. But I personally didn't get very good results with that. Especially if you're looking for a very fine matching, I would suggest a larger box here. So we defined the material. If you want to create sheets, in this case, you come here and you can draw rectangles or circles or things like that, which is what I used here to create my ground plane. These, you can't assign a material if you're designing a zero thickness sheet, but you can assign certain properties associated with it. So for those of you who have taken courses in EM, you're familiar with the impedance of a surface and how it relates to the property. So in this case, you're just going to go ahead and assign an, do I have impedance? In this case, I can simply go ahead and assign a perfect electric conductor if I want for the ground plane, or I can assign a finite conductivity if needed as well. Now, one thing we haven't done yet, and I'm going to zoom in so we can see it, you have to go ahead and provide an excitation for this problem. In practice, it's going to be your BNC connector that you're using. Here, we are going to go ahead and create a wave port. A wave port, and I'll zoom, I think it show up here. This is how the wave port is set up. I click on this wire here. You would see there's a vector that goes from the center to the edge of that circle, and it creates a wave port on this boundary, which excites the aperture. The wave port, you can't leave it open, so I've also created a cap that goes right beneath it. This setup takes care of all the hardware, say, we have, but we still need to define that boundary. We created an air box, and the material inside it is free space or air, but you have to define a boundary for it. So what you see that I've defined here is a boundary that HFSS developed a few years back, known as Phoebe, which is a finite element boundary integral. It effectively creates an infinite space by matching the impedance of the whatever is radiated there to the free space and radiating it using boundary integral equations. This approach is much more accurate. There's another approach known as perfectly matched layer, PML, that was used commonly in the past, but Phoebe is much more efficient. So this is the way I set up the file that I shared with you. Similar to other software like Keysight that you may have used, you have to also go ahead and define the frequency to analyze it. For all software that use electromagnetic models, you always want to make sure your mesh frequency is set at the highest frequency. So in this case, I set it up to be at 500 megahertz, and I defined a couple of sweeps that I wanted to have. The sweep here was that which I used to plot the S parameter, which is typically what you would see on your nano VNA or your ENA if you do the test in the lab. Then if you want to see radiation pattern at certain points, which is what I wanted to do, I also defined a couple of discrete frequency sweeps. So this is at the UHF and VHF bands. And once the simulation is set up, in HFSS, you come here, there's a nice option, which is validation check. It checks for any issues before you run your simulation, and then you can just go ahead and run your simulation results by clicking on this Analyze All. So one thing that I perhaps should have mentioned earlier, the file I shared with you is an archived space, and this is commonly the way we share these types of files. ADS has an analogous archived version, I trust, if you've used it. Here, if you want to send a file to a colleague of yours, make sure you archive it. It archives the file, including all the results, and creates a zip file that you can send. And of course, same way, the file I shared with you, you go ahead and restore it so you can unopen that archived file. But anyway, it would contain all the results, and the results tab here, hopefully, not available because I did not. Okay, so I need to run it again to show you those results. But if you want to work on this HFSS file now, and if you have any questions, I'm happy to go ahead and answer any questions. But I think it probably is good to stop the recording now.